Okay, so as I mentioned a while ago, we cover only 3 topics in calculus. One is limits, the other one is derivatives, the third one is integrals. So we finished limits. However, that idea of a limit carries on into what we do with derivatives, which you'll see as we work through this example or this theorem that I have for you early on. Derivatives, we spent a good chunk of time in that. We'll probably be in derivatives at least until, I would think, maybe around winter break as a ballpark. And then when we come back, we'll do some integrals. We take integrals up until March or so, and then we start reviewing for the AP test. Craig,
So there's only gonna be like one test from now until.
Oh, no. There's lots of little bits of derivatives, but the broad topic is just derivatives.
Will there be like quizzes or?
Quizzes, it just continues on. You know, like chapter 2 introduces derivatives, but then we'll talk about more theorems involving derivatives. Then we'll talk about applications of derivatives, anything you can do with a derivative, we'll look at. Okay, so first things first is we want to look at what we need to accomplish. We're going to talk about the difference between tangents and secants as they relate to functions. So I'm going to take a nice simple function. I'm going to show you what a tangent line looks like. I'm going to show you what a secant line looks like, and we're going to start doing some calculations involving those. We're going to find the slope of the tangent line, which is the gist of what a derivative is. Are you guys done? So first of all, you walk in late to my class, and then you're sitting there talking while I'm trying to do my job. That ain't going to cut it. We clear? Aces. Uh-oh. Talk about the limit definition and how that relates to derivatives. We'll talk about differentiability and continuity. So if you can take the derivative of a function, is it continuous? If a function is continuous, can you take the derivative? That's Monday stuff. And then, of course, you should work on being able to hold your breath for 45 seconds. Not right now. Breathe easy. Okay, so let's start with a tangent line. A couple things. Number one, you should know what a tangent line intersects a function in exactly 1 point. No more, no less. More importantly is this notation. And I don't know what you did in pre-calc last year. I'm sure you've seen f of x notation because we started using that already. But in your other math classes, we talked about random points being at the location x comma y. We're going to change that mentality now, and points are now going to be at x comma f of x. Because f of x is the same thing as y, because we made that transition from y equals blah, blah, blah to f of x equals blah, blah, blah. As opposed to a secant line, which intersects in 2 points. Or more, at least 2. Okay, so you think about, I'll show you an example where it hits it in 2, 3. You think about running a line through a sine graph, it's going to hit it in an infinite number of points. As long as it's not just one, we're in business. Okay, so for the visual learners in the crowd, I've got a nice little demo for you if I can get it to work correctly. Okay, that didn't work well. Let's go over here. Open this. Okay, so let's talk about what's going on in this picture. First of all, the blue thing is my curve. We're just going to call it f of x. The function, or what function generates that curve, is not important right now. It's just some function. You can pretty much guess what it is, but I don't care. Over there on the left, I created a point P, and I drew a tangent in red. So notice the location of P. It has an x value that I labeled as x, and it has a y value of f of x. We good so far? Doesn't matter where P is, it's just some rando point on the graph. Then I moved over some distance. That distance I called delta x. Why did I call it delta x? Change in x, correct. So I moved over some value. And I moved to the right, I could have moved to the left, it doesn't matter, delta x, positive or negative, who cares? Which puts the new x point at x plus delta x. You good so far? Yes or no? Okay, so therefore the y value of that point is going to be f of whatever the x value is. So in other words, it becomes f of x plus delta x. Okay, so 2 points. 1 point is p at x comma f of x. 1 point is q at x plus delta x comma f of x plus delta x. Question number 1, what's the slope of that green line? go to the next slide. Okay, so there's the picture. How do I find the slope of that green line? Come on.
y2 minus y1 over x1, or x2 minus x1.
Beautiful. That?
Yeah.
Good. What's y2?
It's f of x, or yeah, f of x, not close to it.
Mm-hmm.
And then would be minus change in the change in x of x plus the change in x.
Yes. Well, we're going to do it the other way around. The only reason I'm doing it the other way around is because it'll be something that you've seen before. You're 100% correct. But if we do it again, you'll see once I do that. Okay. Because you've seen that, right? Yeah, you've done a lot of that. Everybody understand where that came from? That's the y value of q minus the y value of p over the x value of q minus the x value of p. Just a straightforward, simple slope calculation. And then we can simplify it because x minus x on the bottom gives us that, which again, you've seen before. And if you didn't pick up on it earlier, my goal here is to find the slope of the red line, which I can't do yet because, or I can't do until we get into calculus because there's only one point on that red line. If there's only one point on the red line, we've learned to find the slope of a line given 2 points. Only 1 point, how am I going to do it? Now we need to change the calculus. Calculus will allow it to do it, allow us to do it if we're sneaky about it. Okay? So that's the goal. Now, how am I going to use this to get the slope of that line? What happens if I take Q and I move it over towards P? What's going to change? I'll show you what that looks like for the visual learners in the crowd. Let's stop it there. What's changing as Q moves down the function? Now remember, this could be any function. It doesn't have to be a function in this shape. So yes, the slope is decreasing or becoming less negative. Those things are happening. But in general, what's changing? Regardless of the function. Yes? What else? What's happening to change in x? Speak louder.
It's decreasing.
It's decreasing. How far do we want it to decrease? To
B.
Correct. So if Q slides all the way over to P, what happens to delta x?
So there's no difference. There isn't a delta x.
Correct. So what's it going to go to?
0.
Good. And what's it called when we take something and send it to another number? You just took a test on it.
The limit.
It's a limit. Correct. Very good. So as we continue to slide Q along that curve, delta x is getting smaller. All this other stuff is changing too, but we don't care about it because that's dependent on the function. This is what we care about. This is getting smaller and smaller and smaller, and the slope is changing, which is good, but eventually as Q gets to P, now all of a sudden, boom, they match up. So the slope of that secant line becomes the slope of the tangent line. So if I can find the slope of the secant line, which has disappeared, as delta x goes to 0, then I have the slope of the tangent line. Which gives us that. Okay. The slope of the tangent line will be equal to this thing after you take a limit as delta x goes to 0. So we're going to continue to shrink delta x until it gets to 0. When we start talking more specifics about derivatives, we will have 3 properties of derivatives. This is the first one. It's the slope of the tangent line to the graph at a point. Okay, so let me explain something too. This is important. Without the limit there, we just have the slope of the secant line. Okay, that's a calculation that Colin did. When you put the limit in there, now all of a sudden it becomes the slope of the tangent line. Green, red. Okay, are we good? This has got to be important because it's in a blue box. We good? Okay. Question? Oh, okay. That's the hold on a minute. Not the I have a question. All right, so let's look at an example. Now, some things are going to happen in this example that are going to make people uncomfortable. I'll explain more as we get towards the end. But you're used to, up until this point, you're used to doing a slope calculation and always getting a number. It's either positive, it's negative, it's zero, sometimes it's weird and it's undefined. But for the most part, you get a numerical value. You'll see what happens when we do this. Maddie, what can you tell me about that function? Good. Does it open up or down?
Up.
Why? Say again. It's positive, right? I just didn't hear what you said, that's all. You weren't wrong, I just didn't hear what you said. Okay. Parabola, it opens up. We can figure out a whole bunch of things about it. We don't care. We just have a function. I want to find the slope of the tangent line to that curve at the point 4, 40. They won't always be phrased this way. Sometimes it'll just say at the point x equals 4, and you're going to have to find that. How would you find the 40? Yeah, plug it into the function. Good. I saved you the hassle. We got that. Then we're going to go on to part B and write the equation of a line. What are the two things we need for the equation of a line always? Point and slope. Good. We'll get the slope from part A. We already got the point. This will be cakewalk after we finish part A. Good to go. Now we apply the formula. And it does get a little nasty. Okay. There's the first step. Now while you're copying that down, you also want to ask yourself, self, where did that come from? So I'll ask you, where did that come from? Oh,
So like the equation itself is f of x plus change of x. So you put, since it's 3x, you put that in as x, and then it's 3x squared, and then you put that in for the 2x and 2x, and then it's minus f of x. So just subtract that.
perfect. Okay, the first part, these first two terms are f of x plus delta x. Go to the function wherever you see an x, put in an x plus delta x. That's f of x. I can't stress enough, and I should have stressed it more, how important these parentheses are. Okay? In fact, I would go back to the blue box formula and put those, make sure there's parentheses around your f of x. Because it's a difference function, you're always going to have a minus sign there. Common mistake is people forget the parentheses, and then all of a sudden you're not distributing that minus sign. Okay, so put the parentheses around that, we'll be good to go. Noah, let's stay with you. What do I do first to simplify this bad boy?
Factor it all out.
Good. What's x plus delta x quantity squared?
X squared plus 2x delta x plus delta x squared.
Beautiful. So I did that, squared it first, and distributed the -2, and distributed the minus sign to get rid of parentheses. Distributed to 3. So steps 2 and 3, basic algebra. Distributive property. Next question.
Could you explain, like, putting the function into delta x again?
Yeah. So we go back to the concept of f of something.
Yeah.
So let's say f of star. What does f of star mean? It means go to the function, wherever you see an x, put in a star. So f of x plus delta x is a little weird because the function's already going to have an x in it, but it means go to the function, wherever you see an x, change the x into an x plus delta x,
Okay.
and that gives you your function. Okay? Oops, that's a dot. There we go. If you did it correctly, when you start to distribute things, stuff should disappear. And I neglected to mention something. At the very first line, after we plugged and chugged, sorry, we didn't plug and chug, that's what I wanted to mention. We should have plugged and chugged. I didn't bother because I thought maybe it didn't warrant discussion, but why doesn't plugging and chugging work here? Yeah, it'd be over 0, so that's no good, so now we have to algebraically manipulate, which is what we're doing here. Negative 2x cancels with 2x. Negative 3x cancels with 3x, or negative 3x squared cancels with 3x squared. And we start to clean that up a little bit. Also, if you've done it correctly, hopefully everything has a delta x in it. Because I want to get that delta x out of the denominator. Does everybody understand what I did to go from step 3 to step 4? Yes or no? Canceled, then factored out a delta x. Kelly?
For the last one, at the end it says 2x. Shouldn't it be just 2?
Good catch. You're right. That is a typo. So we'll fix it by doing that, which was a dumb thing to do because when I do this again, it's going to go away. Yes, that should just be, I'll just stand here and cover that. That should just be a 2. I got a typo there. Also, get in the habit of factoring out a delta x. Don't just start canceling things out. Factor it out, then cancel. Okay. So I got down to 6x plus 3 delta x minus 2. Then I took the limit. So what happens when you plug 0 in for delta x? The 3 term disappears, goes to 0. And I'm left with this. And this is what's going to require some explanation. That's different, I think, than anything you've ever seen before. You've always calculated slopes and gotten numerical values. This is different. I have an equation for a slope. Well, why? How can I have an equation for a slope? I need a number for a slope. If we go back to this sketch, though, and I grab P, and I start dragging it around the curve, notice what happens to the slope if I change the point. It changes. So steep slope. What about the slope there? Right there. 0. Good. Negative slope. Over here, slope is 0. Positive slope gets bigger and smaller. So the slope is going to change depending on the x value that you choose to represent. In this particular problem, we chose an x value of 4. So I take this and plug in 4. And I get a slope of 22. Okay. So at that particular point, the slope is 22. Well, there's other points on the graph. In fact, there's an infinite number of points on the graph. For instance, this is the original function. It passes through 0, 0. So what's the slope of the tangent line at 0, 0? I come down here, plug in 0. I get negative 2. It's going to have a different slope. The slope is different everywhere. Question?
Yeah. So you just plug in that.
Just plug in the 4. Say what?
Why the 4?
Because that's what the problem originally asked for. It said at this particular point, 4, 40. Okay, so let me stop for a second to make sure you're understanding. Are we okay with this? Because again, I understand if it's not okay because this is a fairly new concept. The idea that a slope isn't a numerical value, it can change depending on the location. Okay, pretty much the basis of what we're going to do involves that. Is it possible to get a slope of a tangent line that's a constant? Yeah, we'll look at that. But in this particular case, it's going to change. Now we did the hard part, so therefore, what's the equation of the tangent line? Good. Plug in the point, plug in the slope, we get that guy. And leave it in that form, don't multiply it out. You don't need to get all fancies in your pansies. Okay. We're going to continue to do this calculation using the limit function, or the limit equation. By the way, that limit equation is considered, or is called, the formal definition of derivatives. So you'll see on quizzes and tests, when I ask you for the formal definition of derivatives, you're gonna come back to that difference quotient with the limit in front of it.